ahead and record this one too. So what we're gonna do that like the last time that you know that when you go ahead and look at that you, especially when it comes to the syllabus says that there are several sections that you have to cover, that discussion and your assignment, one assignment per week, and 2 quizzes, and 1 midterm and assignment, final exam. So last time what we did was that pretty much that discussion part, even though that it's counted towards the final grade, I made it that optional. If you want, you can go ahead and then do that one. Whether you do it or not, I'm going to give the full point for that one. Okay, so I'm going to do that one. Same thing, same format, keep this time too. And when it comes to the assignment, if you go ahead and look at that one, there are 2 parts pretty much like last time. One part is like I had to write the R codes, the other one programming part, the other part is writing part. So even on that one, I made that writing part optional. If you want, you can do that one. In that, if you put these 2 pieces together, it's going to be that very nice piece of work at the end of the day. But it's an optional. So whether you do it or not, that for that particular part, you're going to get the full credit. So I'm like try to that make your life easier. Plus, even though that we keep the deadlines, I'm not going to be very strict to the deadlines. Remember that you finish your homework, just turn into me. Then in that way, I can grade and send it back to you. And in the previous class, that some homework I'm still grading. Okay, don't worry about that one, since that we have given like a whole this week for them to finish all the assignment for the last class. I'm talking about analytics 600 class. So in that way, I'm planning to send that official grade next Monday or Tuesday. So you can see them on that side. Plus that when you're done on your homework can turn into me, and then when I grade and send it back to you, you know that where you stand in it. Okay, it's not a big deal. So we keep some same kind of like a very flexible format for you guys. If you have any question, anything, that you can email to me, you can call me, you can text me, and you can set up that one-on-one the sessions that go through that material. You can do so many things and get the best use of me, because that I'm available pretty much all the time, except for teaching these 2 classes. And one more thing that I have to tell you, that this Wednesday, we are planning to have a like like in the last time that normally Wednesdays we're gonna have office hours. This Wednesday, coming Wednesday, mean like a day after tomorrow, I'm gonna be out of town, so I'm gonna keep that office hours on Friday. Okay, Friday sometimes you have some commitments on that day, but doesn't matter. Even if that nobody's gonna show up, I'm gonna record everything and then upload to the system. In that way, you're not gonna miss anything. So I'm planning to keep that office hours Friday pretty much same time, 5:30 to 6:30 or 7:30 in your time. Okay. So because of, I had to be out of town. Yeah. So that's pretty much it. And then I think that we continue the and when it comes to the homework, this time we have to cover chapter 8, chapter 9, chapter 10, chapter 11 from the same textbook that we used that one. So you don't have to worry about chapter 12. Okay. So and when it comes to the assignments, you have assignments in addition to that one, your assignment, quiz 1, sorry, the quiz 1 based on chapter 1, chapter 8, I'm sorry, chapter 8, quiz 1, chapter 8, these questions. Chapter 8 review questions would be your quiz 1. Chapter 9 review questions would be your midterm exam. Chapter 10 review questions would be your quiz 2. Chapter 11 review questions would be your final exam. Okay, so in another way that let me see. Let me open up this one here. So when we go to the week 1, Okay, I can make this one. I think week one quiz. Let me check. I'm gonna check on my side. Okay, that's okay. And see whether it's already uploaded. Yeah, it's good to go. Yeah, I think I can make it available. Both. This one go to assignment. Edit assignment. Week one assignment. Yeah, see, you're going to get shape that way pretty much. So in that way, I think I can go ahead and then make both available. See? Okay, now you can see on your side. Okay, you can see both of them. Okay, so all of that our lectures are recorded and then made available for you. That in that way that you're not going to miss anything. Okay, so let's go ahead and unlike last time, we don't have that 2 chapters per week. We have only 1 chapter per week. It's easy. Okay, 1 chapter per week because we have laid down a good foundation in previous class for us to move forward. Okay, so let's see. Let's see here. Let's go ahead and see what you have on chapter 8. Look at, you can remember in chapter 6. Chapter 6, not actually chapter 6. Here, see, chapter 5, we fitted the empty model. We fitted the empty model. Chapter 5. Then we talk about it's all the characteristics. See, all the properties and characteristics or quantify that we quantify error, we quantify that all the parameters, and then we talk about it. 6 and 7, what we did, what we systematically fit in a model with the explanatory variable. We added explanatory variable for X systematically. Now in 8, what are we gonna do? We're gonna add a quantitative explanatory variable. See? Quantitative explanatory variable. See, model with the quantitative explanatory variable. That's what we are planning to do over here. See, model with the quantitative explanatory variable. See, in previous chapter we figured out how to add an explanatory variable to a model. See, we explain thumb length using sex and using height, coded as short and tall, or short, medium, and tall. That time that particular explanatory variable was, but categorical. Okay, categorical. Now this time we're gonna add like a quantitative explanatory variable. See? We add more groups. We reduce the leftover error, explaining more variation in our outcome variable. We did all of these. See, you can remember the 2-group model. It's like a kind of a review. We can remember that what you did in tiny fingers. See, if a short and tall. See, 5 to group like that. X can be that considered as like a what, like a dummy variable in this scenario. You can remember we had that broader discussion. And see, and in this case, how X can be coded. See, X in this one can be coded as a 0 or 1, 0 for short, see, 1 for tall. So we wrote the equation too. See, V naught and with this setup. See. So Y would be thumb length. See, thumb length. B naught. See, then V naught, the mean thumb length for the group in variable. See, for the when group in variable is 0, then it's in short. If you're going to tell that it's going to be that average thumb length of the people in that short group. See, short group. Okay, and this one is the average thumb length of the B1. B1 is that the gap between the increment to at. See, increment to add on when the group in variable is 1. See how much you have to increase that the average in order to get the average of that thumb length in this group, people in this group. That's B1. Sometimes we call that one slope. This one intercept. X would be the what the group in variable whether that kind of fall that which that belongs to a 0 1, the way that it's been coded. 0 should be people short group, this one tall group 1, and E is the error. See, error. How of the model's prediction is also called the residual. See, residual law that normally that even that error can be considered as like a term that we utilize in population, but interchangeably we're going to use the residual error or deviation. Another word, deviation. So let's see. V1 is the increment 2 add-on for short people. So this we can remember that we divide this into 2 groups. When you have a like a height, that's a quantitative variable. We convert that into a categorical variable. You know how to do that one. You can use what? Entile. Using that quantiles, you use the entile and then two groups here. We are using 2 groups. Okay? Entire 2 groups. So that's going to put that one. Then instead of that one, what they are thinking then, they are not planning to use that quantitative variable. They want to use that height as it is, see? Quantitative. When it comes to quantitative, our that all the data points are scattered like this. This one called the scatter plot. You know how to draw a scatter plot. We had that discussion too. See, quantitative versus quantitative. Earlier quantitative versus categorical. In the beginning, quantitative versus nothing. So we have 3 models already we built up now. Systematically, we came to the regression model. When both our outcome and explanatory variable, both the outcome and explanatory variables are quantitative. We need a different kind of model. We can't use the mean as a model because we don't have a group. Instead, we're using line, the regression line. So here we're going to talk about very important procedure, okay, statistical procedure called the regression line. Regression line even coming under that machine learning as well down the road, and under the supervised machine learning. Those are parametric. Parametric means parameters are involved, data naught and data 1. Okay, when then some people they don't like to work with the parametric setting. They'll go to non-parametric. That's what called the decision tree. That's the one that actually that the one you have already seen that I was working on some project on that one. See, decision trees or something like that. See, that kind of a setting. See, like that. Okay, that's another version of a regression. Instead of using regression, people are gonna jump into the decision tree. That if you're gonna learn this stuff down the road and then write the codes. See, for the given data. See. It's a supervised. Supervised means like you being given in machine learning, you being given that both this one also supervised. Regression also, regression also supervised learning. It has been given, see, it is being given in this case that you've been given that input and output both that X variable as Y variables data. With the aid of that one, you're going to build up a model, and with the aid of the model, you're going to make the prediction about that whoever enter into the system. You can make a prediction about that one. Anything like that. If you want the hiring process, the patients, that illness, anything can be predicted in businesses that they're going to strategize anything. Then they come up with the new strategies, everything that they're going to predict that ahead of the time with the aid of this kind of model. That's why regression model is important. Yeah. To show you something. Show you something to feel. It's coming under this one. See, it's coming under this one. See, all artificial intelligence coming under the there are several branches in the artificial engineering. Everything coming under this big umbrella: machine learning, neural network, language processing, expert system, vision, speech, planning, robotics, everything. Under this one, you have a deep learning, supervised and unsupervised. Under the supervised learning, you can see regression. Regression. Here we're going to lay down a foundation for regression. Later on, we're going to go to simple linear regression. Then later on, you go to that 420, that multiple linear regression. Then you keep going with that 625, 30, that you're going to go to logistic regression like that. And that's I told you, decision trees, another format of regression. See, this is called the parametric setting. This is a non-parametric. You don't use the distributions. Here we use the distribution. Here we don't. It's easy. It's a machine learning setting. See, decision trees and non-parametric supervised learning algorithm. Okay? So you're going to learn all this stuff. So we are systematically laying down a good foundation for you to learn the heavy stuff down the road. So as I mentioned earlier, that when we come back to this, the basic one, that here, see, thumb length has been explained by the height. See, look at these, all the dots. These dots. Now why we use a straight line? Why we cannot combine these two line segments, two at a time? This one, these two, these two, these two, and these two. Can we do like that and find some kind of a model? Yes. See? Some kind of model, we can build up something like that. But in the primary stage, we don't do like that, because those are heavy stuff. Heavy stuff we're gonna do a certain way down the road. You can do. See, so many books on my table. So those are called the spline. See, if you do like that, spline regression. We don't go to that one in the beginning. Later on, you might be thinking, why we not going to get some kind of a curve to fit in this one? It's not necessary all the points to be on that fitted curve. Some may be off, some may be on, some may be above, some may be below. Doesn't matter. See, can we do like that? Yes, those are polynomial regression. Those kind of a thing, we don't get into that one right away. We come to that one like in 420. In the primary stage, we were thinking about try to model this one instead of this scattered all over the place of this data. We are planning to that model with some kind of a straight line. So which straight line is the best fit for this one? That best fit has been decided through a mathematics. Actually, they were using mathematics, and they decided there's a line which has like a minimum error, minimum sum of squared error, which produce the minimum sum of squared error would be the best fitted line, best straight line, best fitted line, which gonna go through the center. Center is nothing but the mean of height and the mean of thumb length. This is a center or centroid. We're going to call that one centroid. Through the centroid, you can draw, see, infinitely many lines. But by using a certain method called the least square technique, we come up to a conclusion that this should be the best line. The best line is determined by its two parameters who are responsible for drawing this one. In order to draw like a straight line, you really need a what? It's slope. Slope is nothing but the inclination. Inclination of this one with the positive side of this height, positive side of x. That inclination, which is the slope, and the other one is where this gonna go and hit on this the y-axis, thumb length. Okay? When height 0, still they have a thumb length. It's not realistic, but mathematically it's okay. See, height is 0. That means that person is not even born, but they were talking about the thumb length. See, unrealistic, but mathematically, abstractly, it's okay. Practically, empirically, not. So you have to make sure that when you deal with some models, one model is very abstract. That's a population model mainly. And on the other hand, the other one is empirical model, practical model. Practical model, most of the time they were truncated. See, data truncated. You don't get from here. See, that doesn't make any sense. But if you want to make that one sense, that you can do some kind of adjustment, we're going to talk about one down the road. So you get the best fit for this work. How they determine that the best fit has its own that own slope and the intercept. Intercept simply we call the intercept for the y-intercept. In addition to that, and there's an x-intercept as well, but we don't talk about that one. Intercept means that y-intercept. So you can calculate x-intercept and y-intercept. You don't calculate. You run regression. You simply run and get the values. That's it. Very easy when it comes to. But you have to have a clear idea what's going on over here. So this one is a straight line. Straight line can be explained by what? See, y equals mx plus b format. You can remember in mathematics. See? B is what? Intercept. Here in mathematics, they write this format. The slope first, then the x variable plus the intercept. But in statistics, we write the intercept first, b naught first. Okay, let me see. They have that. See, no. See, they write this intercept first, then the slope, then the x variable. This is not a dummy variable this time. Okay, this time this is not dummy. This is height. This is thumb. That's it. This is the intercept. This is intercept, which means like what is the height when height? Sorry, what's the thumb length when x height is 0? And this is what average rate of change of thumb length with respect to height. The increment in one height, the 1 unit increment, how much that the thumb length has increased. It's called the slope. It's called the marginal value. This is the marginal value. In another way, the marginal value, like a marginal profit, marginal losses, see? Marginal cost, same thing here. See, marginal thumb length. That means that how much thumb length has increased for that increment in height, 1 unit in height. That one. So average rate of change of thumb length with respect to height. Another way. You can explain that one in different ways. See? So this time, see, same formula. See? So thumb length, see? Thumb length x equals 0. See? And b work, see? Increment to add to on each unit of x. See? Height in inches. And error. So as we see over here, when you get this model, this part is called the estimated part. See, this part is the equation of the regression line. This part only, not the error part. This is y hat. This part is y hat. So anything, any point has a y and y hat. See, so see, this is y. This is y. This is its corresponding y hat. This is y corresponding y hat. Y corresponding y hat. Early in the so that empty model, can you remember? You don't have this kind of a slant line. People thought in the beginning, everything can be measured with respect to the average, their total average. That time, in the beginning, we didn't have this kind of a slant line. But later on, somebody noticed and thought about, okay, no, when we work with a slant line, how it works. See? So this time, see, same thing, see. Predicted value or estimated value and the gap. See, the gap called the error. That is also, see, y hat is nothing but this part. From here to b naught plus b1 plus x. For a given x value, you can calculate the estimated y value. But you know the true y value. Then true value y value, if you know the, now you might be thinking, why, if you know the true y value, why you really need the estimated value? No. Not for us. This one for someone, the seventh person who's going to add it to this one. By looking at their height, measuring the height, we can estimate his thumb length. That's why we really need that. This is a model. We are built-in up a model. We are built-in up a model. By looking at the height of that particular person, you can just simply say estimate by plugging into this one. You're going to based on this one. Without measuring the thumb length, you can say on average that particular person has a thumb length this much, something on that line. See, let's say somebody gonna add over here and then go and get that one, see, extend this one and get the value by plugging into that formula. We don't do that one. We use the function predict. Predict will do that one. Yeah. Right. That's the whole, see, now that's why they try to explain this, basically that B naught is nothing but B, see, Y is Y, see, Y I means Y, B naught means like a B, B1 is same, X means, see, this is the mathematical model, this is a statistical model. The difference is, look at here, you can see clearly, as I said, see, empty model, see, with respect to its now the height model. See, it's the empty model. And then you have another model, empty model and height 2 model. Can you remember? With another model too, height 2 model. That's a categorical model. See, in this particular one. See, height 2 model. Can you remember? You're going to put the short and tall. And these people see 56, 59, 60, 63. This one looks like 63. This, oh, sorry, this one. So this one 56, 60, no, not 59. This one 59. See, is this 59? Should be, what are the 56, 60, 61, I think I can remember. No, yeah, they pretty much the same. 56, 56, 60. Why did I say 60? I think we had a 60. I can remember. Let's see. 56, 60, 60 years. I think our data points are 50. Let me check. 56, 60, 61. Oh no, that's not for this one. That's for the male and female. Okay, that's not male and female based on that one. So anyhow, we have that regardless of male or female, now they have been that divided into short and tall. But the same data set, we have a 56, 60, 61, 63, 64, 63, 64, 63. This is 63, 64. And this is 68. This is 60. This is 60. This one is the 63. So this is 56. 56. We have data 56. Last time we divided this one based on the gender. Now this time we divided this one based on the height, but it's a categorical model. See? So this one 56. This point 60. This one 59. This one 63, 64, 68, right there. And on the other hand, the average, what would be the average? Is that average? The average, this one average here. The average look like a 65. That's 65. Again. Let me check this. So you have a 56 plus 60 plus 63. Yeah, 59.6666. So almost 60. Those three. If you get these three, this one should be 63. No, hold on. This one, not right. This one is 59. 59 plus 64 plus 68 divided by 3. 63.444. which is 64. See, that's the 64. But when we have a based, if you're going to divide this based on male and female, you can remember 59 and what? 59 and 65. For female, you have a 59. Male, you have average 65. Now, this time, this based on short and tall, they were being mixed up now. So this time, you're going to have a here around, this one is 59 point something, almost 60. This one, like when you run that, you can see that one, it's easily, we don't have to worry about that one. But if you run this one on R, you can see. But we don't have a sandbox over here to run. But okay. So anyhow, see, this one 64. 64, this looks like a 60. Same thing. See, the gap is like a 4. Let's see that sometimes that later on they might gonna show this one. Okay. So see, that's the same thing they show over here. Now it's been like this way. See? Height in groups, height in inches now. See? See? Height 2 group. See? Still you use this one. This is plain heavy roll, okay? So you have to draw this line all the time. Average, see? The overall average, the grand average, grand mean. See? Grand mean was 62, you can remember 62. Regardless of they being short, tall, male, female, 62. If I can remember 62, that one. See? See? That's a SS total for the that height 2 group would be the same as SS total for the height. Doesn't matter. Because the SS total means like you're gonna SS total is measured with respect to what? Each deviation square with respect to the this, excuse me, the grand mean. Grand mean. They both the same. They both the same. See? Either this one, or empty model. Empty model, can you remember? That's the same as empty model. Empty model or height 2 group or this one, they three of them pretty much produce the same result for the SST. SST. See, here SST, here SST, and in empty model SST. All these the same. Okay. See, what could make a prediction better? Less error from the theta to predicted based on height. Less error. Okay, you know that. That's a little bit. We'll look at it and then see. Now regression line as a model. See, filling this one. See, what does the blue horizontal line represent? See, this one, blue horizontal line is nothing but the mean of the thumb length. The prediction of the empty model for every possible value of height. The prediction of the empty model. That's the prediction of the empty model. You can remember. Doesn't matter. It's been scattered like this. Okay. So what they are trying to do is this one. Okay. I'll show you what they are trying to do. Okay. LM is this is not a big deal. See. So they're gonna just modify this to fit the term as a function of height. See? Tiny height. So that this time, see, height and this one. See, like this. Okay. So you're gonna have this one. This time you have a thumb here and see. But height and data equals tiny fingers. That will give you B naught, B1, B naught, B1, B naught, B1, then B naught, B1, fitting into that one plus. See, it's a fitted model. See? Fitted model. Y represent thumb length, X represent the height. See? See? What does the minus 3.16 mean? 3.16. Here, that's the y-intercept, the prediction thumb length when height is 0. When height is 0, they're going to predict that the thumb length should be this much negative value. So it cannot be negative value. You can get rid of the negative value later on. We're going to talk about that one too. See, we can make some kind of adjustment. Then we can do the adjustment. Okay. Number of millimeter, number of lenses, small, 0.98 is. That's the slope. Slope, that's the explanation. This is the number of millimeters to add to thumb length for every inch of height. Every inch of height, see how much thumb length should be added. See, it is positively. See, it's a they look at that the way that we saw that they were positively correlated. Positively correlated means slant to the positive side of x axis. Okay. You can add this one. See, all the R is pretty smart about knowing which model to fit. It won't always do the right thing. If you code the grouping variable with the character strings short and tall, R will make the right decision because it knows the variable must be categorical. But if you code the grouping variable as 1 and 2, and you forget to make it a factor, R might gonna confuse and fit the model as though the explanatory variable is quantitative. You have to be careful. See? Other than this one, when you're gonna categorize using the entile, entile we're gonna do two steps. First time entile, and the second one you're gonna factor, and then you're gonna change that these numbers, default number, they're gonna create the numbers. Then you're gonna divide into two groups. First group they call 1, second group 2. Rather than that one, you can convert. You're gonna replace 1 with short, 2 with tall. Okay, you can do like that. If you don't do like that, what's gonna happen? If you take this one, thinking that you are doing a categorical that fitting this one is a categorical variable, it won't do that good job. See, if you make a look at the variable height to group and group num, they have the same information. Student 1, 2, 4 are in one group and student 3, 5, 6 are in another group. If you feed the model with the height to group, see, and call the height to group model, and group num n is called the group num model, we would expect the same estimate. Okay, let's try it. We would expect the same estimate. Let's see what's going to happen. See, height to group model. Height to group model, you're going to have here thumb. Here, there. I'm going to get something from here. And instead of height, I'm not going to go to height. I'm thinking the categorical now. Height to group. Group. Okay. And the other one, group. This one with the other one. Height to group, instead of that one, I'm going to go to group num. Group num. This one now, this, and see whether they both produce the same result. See, they know these are categorical. We know these are categorical, but the machine doesn't know unless that you have that specifically mentioned and say, make it factor. Okay. So, here, look at, see. Look at what happened. The scale, the ratio gonna be the same because it doesn't matter regardless of how you have taken that one, ratio gonna be the same. But look at your intercept. They were completely different. You are expecting them to be the same. We would expect the same estimate. Let's try it. See? One is 4.667. That's okay. 59.667. The other one 55. See? Should have been the same, but it's not. See? No, see. So this one, if you're going to fit in into this one, 59 point first one, thinking that height to group, this is a categorical variable, Second one also categorical, but he has misunderstood as being a categorical. He thought that it's a numeric. Yeah, see, 59%. Y is a thumb length. That's the short group's average thumb length. See, and increment to add to tall group, and 0 for short and 1 for tall group, and difference between model prediction and thumb length. See, you know that one. See, model estimate is so different because the model does not treat the value group num as representing group. It's not groups. They think it is a number. These are numbers. See, they are numbers. See, see? They are numbers. See? So you can record that one. See, if you record and run, they should be the same. See, you have to have the same. You're gonna record. Record means you're gonna replace that one. See that group short with 1, tall with 2. Otherwise, he think this is what? This is regression. They think this is a two group the model. This is a regression model. They're gonna mistakenly think this is a regression model because they think these are numeric. Okay, to avoid that one, you either go to entire and cannot remember in several homework that we had that one. I'll show you something. Okay. This one. Yeah, two, no. See, you can remember, see, the entire, then automatically they're gonna get 1, 2, 3. See, that's the default. I'm gonna replace that one with this one. See, like this. If you do like this, they're gonna think that particular 3 groups are definitely categorical. Otherwise, they think these 3 numbers like a word mistaken as like a numeric. That's why they're gonna tell us to recode it. Either that you're gonna do this way or recode. You know what I mean? Not really doing this one way of doing that one. I think it should be somewhere here. Maybe code that one too. See, yes, this example, the way code this we can show. See, this entire one and convert to factor. See, say please get these 3 numbers as a factor plus that they've been replaced by for different numbers. The same way you can do over here and say short and tall. Plus, I'm going to show you the other one too. Okay. Let's see, should be somewhere. Factor. Yeah, you can easily replace that one with that one, but I'm trying to show you because it's easy to show you. I think this one we did, this one is the report to the sample. Yeah, this one is the resample. That's why we see the resample. Recode that one. Okay, recode and run that one. Sorry. Recode and then run, then you're gonna get this different result. Now they have get into the full data set. Full data set is like this. It's going like that. And then they can draw the that GF point, see, scatter plot, and then you can get the best fit, best fit, best fit. See, that's the one. See. GF point will give you the thumb to height. See, this one. See. GF go to the linear model. When you put the linear model, it will give you the that tiny fingers. Okay, full fingers. I'm sorry. Here, full fingers. Full fingers. Like that, and then best fit. See? This might not gonna be the best fit. Okay, we're gonna talk about this on a large scale later on. See, it's like a cluster. If it's cluster, there's no any correlation between these two. Then we can talk about some kind of a correlation between these two. See, whether there's a, what's the strength of the relationship between these two can be explained by the something called the coefficient of correlation. We mentioned about that one. Can you remember R squared PRE, proportional of reduction in error? You can remember proportional reduction in error. We took the square root of that's nothing but the coefficient of determination. We take the square root of that one. That's the correlation between these two. Then we're going to talk about how to build that correlation as well. Okay. Making prediction. You can make a prediction about that. See, this part is the prediction part. When you make a prediction, see, if you put the somebody with that height 70, you plug in into this one, but you don't have to do like that way. See, you can make a function. You go to the model, you get the height model. See, here they were looking for the height model. Okay, in the previous one, let's say that they have a height model. Point, see, height model. See, some length with the finger data. See here. So here, see, length, height. I'm gonna go to height. Okay, data, fingers. Height model. If you go to the height model, and then if you want to find that is, see, this one is so too that graphical representation. And here, if you need that, see, you can make a function out of it, see, and you're gonna say the height function. And height function, if you put the 70, that will calculate that one. See, by hand, you don't have to hand. See, you have this part. When you ran that one, you got the B naught this much, and put it back to here, and you get this part. That's the estimated value. See, what would be the function of predicting part is this part. Then predicting part you take out, and then for a given height, it's already for a given height. See, height, any height. They say that somebody with the 70 inches height, you're going to plug in into that one. Manually, you did that one, 60.0. You don't have to do like that. 70, would that be a part of our data set? Would that be a part of our data set? No. Can you remember nobody with that our data, when it comes to that draw that graph, pretty much gonna go from the shortest one 59 all the way up to 56 to 68. No, 68. That we are looking for somebody with that height 70. Can you remember our graph? If you go back to the other side. This one, this one, this one. This one. I think no, sorry, that this for the whole data set. Whole data set. What would be the shortest one? The 70. Would they see? We have a 70 already. See? This one we have a 70. Somebody with the height 76. Several of them. Let's say anybody in between. See, somebody in between. What do you think? See? Somewhere here. 70 point, let's say this one 70 to 5, 70, 72.5, 71 something 0.75 or something like that. Somewhere here. See, it's not been a part of our data, look like. See, there are no dots, but still you can calculate. But if you need that estimated value for the x values already in the data set, they are corresponding that the projection. See, the projection on this one on the line, projection on the line is the estimated value, predicted value. Instead of this value, I'm going to predict this value should be this one. See, but this is based on this model. Model has been built up. That's why we call this one that supervised. Supervised learning means that we give the x value, y value. See, you built up the model. That model you're going to utilize. Unsupervised means you're not going to give this one. You're going to give only x only. They built up something and they predict all the time. Unsupervised machine learning, that procedure. But here anyhow, see, for this one, you can get the predicted value, see, projection on this line. How do you get this line? Based on the least square estimation procedure that they decided this would be the best line. When you ran that one, you saw that its slope and intercept. Based on that one, this would be the best line. See, this is not going to be the best model, but this is the best line that's going to go through the centroid. For that one, we're going to utilize to make the estimated value. See, so you have a 70. 70 is estimated value. You can easily predict by running the predict of this model, height model. You can get the predicted value. I'm not talking about the black one. I'm talking about this, the projection here. Let's say somebody not in a part of that one. Can we get that one? That's why we make a make function. That's what I want to. This is the make function for any value. See, when you make a function, you can plug in any value for this one. See, you make a function for that particular model, any value you're going to see. You built up the function. When you put 70, they're going to take the 70, go inside and calculate like this. Let's say you put the 70.125. It's going to go inside and calculate. But if you use the predict won't give that one. Predict is completely based on that whoever the height that you had in your system. See? Looks like even the 70, they don't look like they don't have what. Maybe they have. I don't know. From this, let me see that. In the graph, I see that 70. 70 heights are here. That's why they're thumbnails. Yeah, but they were not in this first. They were not displayed over here. But anyhow, see, if let's say that if you want to calculate anything in between, look at you use the predict too. See, use the predict. See, predict the height model, and you use the function, make function to height model, make function to height model, and then you calculate. Or you go straight to height model and then predict, and you put the predict, it will calculate pretty much all the values, all the x values correspond to all the heights, estimated thumb length, estimated thumb length. These are the estimated thumb length. See, this all the points are gonna be on the straight line. So the difference between these two is the error. Thumb to thumb, see, estimated thumb, thumb, estimated thumb. They use the height trade. It's not for the height, it's for the given height that they use in that for their convenience. This thumb length, this is y, This is y hat in another way for your convenience. Y hat, y hat. So if the x value is already in the system, see, heights are already, they calculate everything. What the predict? But the predict cannot calculate if you really need something in between. Let's say that you need something in between somebody's height with like a, uh, uh, sorry, this one 64 to this one, let's say that 68.125 or something like that. That kind of a thing not being in the original data, those heights. If that's the case, we have to use the make fun. That's why you have a two types of way to get this done. Make fun for any value, any height. This one only for the heights that are available in the original data set. Okay. And from that one, you select the fingers, go to your data set, you thumb, height, grade, and then 10, select, and then show like this. What are the numbers in the height grade? Thumb length, same thing, thumb length, thumb length, thumb length in millimeters. Now what they're gonna do? They get the height predicted value and versus height. See? Get the predicted value. See, you're gonna see EF point. See? If you make a like a thing that this scatter plot, see? Look at scatter plot gonna be on the straight line. See? Height predicted value versus height. So that's kind of like a rough idea we get. Okay, we keep going. Residual now. See, now resid. See, go to the resid. You can get that one histogram. See, for the histogram, you can make it. I'm gonna come back to that one. Now, see, I'm gonna get like a rough idea and come back. See, later on they get that one, and then they run what? See, supernova for the height model, supernova for the categorical model. See, categorical model, height model. See, empty model. You have another model, empty model, height to group model, height model. See, they are some square. Okay, okay. See, they're the same. See, so here, here. But the way that they've been explained, look at the pre-value, 15%. This is 6%. Height model is getting far better. See, 18, 16. This one 830. Been explained. Leftover 11,000. Here 10,000. Compared to this one, this is much better. Because this pre-value, F value, see? Pre-value compare. This is greater. Here, pre-value, the F value compare. These two value compare. See? This is more than this one. If you compare this value to this value, this should be less, should be left over. The other one more should be left over in the worst model. The bad model, more should be, but the total which came from that empty model stayed the same. See, then let me see. If you see, they call this one, let's say, empty model. Empty model. You can name the LMC. Data. Model. The other one, you can see find two group model. No, the other model. Let's see what the name they were using. One is height model, the other one height to group model. Yeah, height to group model. Group model. Yeah, I to groups. They're gonna put the same name they use for the x-axis. The other one is height model. Height model means it's some height. Mhm. Two group model. This. It's okay. But if you run those three, and compare this value is gonna be on the empty model, height model, this one. Again, they're gonna ask the height to group model. See what is the outcome variable height to group model. Some length, always. See? Some length, some length. And what about the height model? Some length. Look at the total sum of squares for both models. Why are they same? Because of these models have the same outcome variable. And the SS total is always the sum of squared residual from the value of the outcome variable to the empty model of the variable. It's fine. Empty model with respect to the empty. Height to group, height model. Again, the same thing. Free value, comparing the free value. You can compare free value. By comparing, you can get this term. And the correlation, as I said, see, correlation is what? Correlation is the nothing but the relationship between those two. Okay. So what I'm gonna do, this add something to here, see before moving forward. Okay. Let's see. We have here. Let's try to get this straightened up. Right? No. Let me get rid of this one and then in 1 second. So you can remember that we have a different We had I can remember that we had three models, see, empty model, see, empty model, we had an empty model, see, first one, see, empty model. There's nothing on this one. Why all this thumbnail thing? Oh, that one issue model that. So see, no x variable here. See, can you remember when you have about y bar for see grand mean, see, grand mean, see later on, see no x values, see no x variables. So then you can say this is equals, see, equals, but just the model, see, model is what? Average thumb, see, average thumb plus E, see, average thumb plus error, you know what I mean? So that's the same thing we wrote y bar plus E, see. So this is the same thing we wrote y hat plus E. So then we wrote the error, nothing but y minus y hat or y minus y bar, same thing. Y means thumb length minus average thumb length, see? Average thumb. Average thumb. Average thumb. So in R we saw this one very easily. So see, we say the empty model. See, LM, see, and now data fingers. Then you get what? You get beta naught. Beta naught is y bar only. See? That's why we wrote, see? That's why we say that y hat is nothing but b naught y bar. See? Same thing. Average height. Then we measured what? Sum of square total. See, SST. You can remember SST is nothing but SSE. SST is nothing but SSE. So, see, its own mean. See, y bar, these are the y values. See, these are the y values. So the gap, see, these gap errors. See, these gaps errors. See, this is y hat. This is b naught. This is y. See, any y. It's nothing but summation of what? Y minus y bar squared. See? Sum of squared error. Sum of squared error. See? So its degrees of freedom of error is nothing but, see? Look at here. It is how many data points you have? N. See? N. How many data points being utilized in order to calculate y bar? 1. Because of that, it's n minus 1. See? That's how you're going to find n minus 1. See? Degrees of freedom. Sum of squared error. It's same as this one. See, this is nothing but, if you check very carefully this one, sum of squared error is n minus 1. See, n minus 1 times variance of y. See, n minus 1 times of y. See, another way you can say sum of squared total means, if you go ahead and check the variance, if that has been multiplied by the n minus 1, n is the total number of observation 156 or something. And if you check the variance, if you multiply, this is same as that one. See? N minus 1 variance. See? That means degrees of freedom times, see? Another way you can say degrees of freedom times variance of y. See? Same thing. It's the same thing. It remains the same from the model to model. That's the unexplained error from the empty model. See? You get these errors and squared. See, this is nothing but you get the errors, all the errors squared and sum them up. That's the same thing. See, for all the points. Same thing. See? So that's the error that they are trying to explain through another model. Then they came to like a height 2 group model. See, let's say height 2 group model. See? Or we can simply say group model. This one. So this one 2 group model. 3 group model. Doesn't matter. You can still. So this time what they did was that they put here, see, x variable included. Now what is that? Height to group. See, it's categorical. Then here, thumb length always, thumb is y is always quantitative or numeric. See? two group, this one group model or two group model. Length, see, quantitative, count. Then they have something like this. See, you can remember. See, this is short. See, this is tall. See, two groups, and they went to the average. Y bar of short, Y bar of tall, and then they found there. See, the gap B1. This one is same as B naught. This one noted by 0, this one by 1. This gap B1. This one is B naught. So the model they write, see, y equals B naught plus B1 x plus 0. This time, x being either 0 or 1. And y hat means the estimated part. Estimated part for based on that your y, see, estimated part y hat, see. Predicted value y hat is B naught plus B1 x. See? For the short or tall, doesn't matter. See? See? So x has a the 1 for tall, 0 for short. See? So the error, see? Error this time is y minus y hat. See? Y minus y hat. You're gonna say thumb length minus average thumb again. See? Thumb, average thumb. Whose average? See? It's called the group average this time. See? Group average. Okay, you have to be careful, not the grand average. Group average. The last time we subtracted average thumb, group average thumb. We're going to subtract from their own group mean. Group average. Last time we have a grand average. Then you're going to subtract average thumb. You can say grand average thumb. Grand average thumb. Last time. This time error. It depends on that the group. The person is in which group. See, that's the error. That's how you're going to find the error. Based on what? Average thumb. See, grand average thumb is nothing but the y hat. See, y hat, same thing. That's the same thing. I wrote the same thing. Then here also they go and then calculate what? All the errors. See, all the errors. I mean, like regardless of that, it's been in that any that let's say here, see, error. See, this also error. See, let's say this person here to its mean. That's an error. See, error. See? Then you subtract, then you square them and all square them, and then you. See? That's what we call the sum of squares. Sum of squared error. See? See? And on the other hand, that earlier that I had to add something over here. See, if you go to the standard deviation, see, Standard deviation of y is nothing but, see, root mean squared error. Root mean squared error. Or root mean squared total. Same thing. See? Same thing. See? It's another way to that. Look at that. You go to the, you know that from the ANOVA table, you can easily get that one. You saw the ANOVA table, you can get root mean squared error, root mean squared total. Here, see, e squared. See, it doesn't do anything over here. That it's with respect to that one. In addition to then, you have what? Another error. Sum of this one is, see, this one is summation of what? Y minus y bar hat of a short group. See, I'm gonna square. See, I'm gonna say that this is in ys. The other one in tall group. See, yt minus its own mean. See, square. That's how they got that one. Summing, you sum them up. See, sum squared error. In addition to, there's another error. See, another error. It's called sum squared total. It's measured with respect to what? Everyone. See, grand mean. See, everyone with respect to grand mean. You can see that one too. Y minus y bar. Grand mean. Square root. See, another error. There's another error. You're gonna go to sum squared regression. You can remember that one. SSR. You go to, see, from everyone, you're gonna go to mean. See, you have a y mean, y bar, y bar short to y grand mean plus, see, y bar tall to grand mean. That's square. See, that's sum squared regression. Then you can remember their degrees of freedom. Degrees of freedom of error is nothing but n minus number of x variable, x var in the model. Sorry, number of parameters in the model. X bar. Number of parameters. Number of parameters in the model. Okay. And degrees of freedom of total n minus 1 always. And degrees of freedom of regression n minus number of regressors for x variable in the model. Regressor variable in the model. The third model is the one, that regression model is something that we talk about right now. Regression. See? Regression model. Look at regression model. Both are what? See? X, you put the height quantitative data. Y, some length. Again, quantitative. Both are. So this time you have everything scattered all over the place. The scatter plot. Y equals some Um, see, then you have, see, that's the best line. Gonna go through that one, see. So we have a what here, X bar. Here what? Y bar. X9, Y bar. See, that's called the center. That's the center. It's gonna go through the center. So we can easily get that one. See, in R we saw that one, what you're supposed to do. So in addition to see this one, see, we have another line going through this one. See, look at anything. If I'm gonna pick from here, this point, look at this point with respect to this one. And it's been shifted from here to here. And there to there. See, look at 3. See, this one due to total, due to total. See, this one due to error. That gap, that's the error. This one due to regression, being regress. That gap. That gap. See. So see, they all see all away from that. They were not see this point, neither on this one nor on this one. See, away from that one. See, it should have been. See, in the beginning they decided this one. In the beginning there's nothing. In the beginning they have only this one. And later on they go to the two group model. Doesn't matter. Now they go with this model. See, quantitative and quantitative. See, they get the best line, best fitted line. This one is the best fitted line. See, this one called the best fitted line, best estimated line. Or we call the regression line. Regression line. See, estimated. Estimated line, regression line. This estimated line, regression line, and equation. See, equation of the line. Nothing but y hat equals b naught plus b1 x estimated. See, predicted, or another way, predicted sum equals intercept plus slope times height. Yeah, write this one. Something not right in right. Equation of the line. Y hat equals b naught plus b1 x. We made a thumb. So intercept, sorry. It's not right. Something wrong in this thing. something wrong. Right, they were getting distorted. Something. So sum of square thing. So sum of square total is earlier same like y minus y hat y bar squared. Sum of squared error y minus y hat. Sum of squared regression y hat minus y bar. That's it. All these you can see from the when you run the ANOVA table. See? It's right for certain reason. This is not. Not not right in right. Okay. Getting this code. This pen has some issues. I have minus one square. Not right. Something not right in right. Sometimes right's okay, but sometimes isn't. So later on that we talk about the correlation is that key part that I want to talk about that one little bit, the correlation. See, correlation is that correlation coefficient. We talk about that one in different ways. I would like to yeah. So what I'm gonna do, I'm gonna show this one. We'll see, because rather than if I'm gonna write that one, I'm gonna this stuff. Okay, please. Look at we can get the finding R from the right away. Yeah. The Pearson correlation coefficient is the strength of the relationship between the outcome variable y, the thumb length in our case, and the quantitative variable, explanatory variable. See? The quantitative variable means explanatory variable, x height. See? The slope of the regression line between the standardized variable. Another way to look at them, they say this is nothing but the slope of the regression line between the standardized variables. You can easily get the correlation by running, but I'm trying to say this can be get it done in different ways. Okay, so hold on, I'll show you something. Look at see this one. See, look at here that we are trying to get that one correlation coefficient. See, correlation coefficient you can get in different ways. First method, correlation. Okay, I'm gonna show from this one. Okay, think about this is the that some kind of let's go to this one. See this model. See, let's say the correlation coefficient using the co-function. So this is your arm length in our example. Okay, this is like a weight. Oh, sorry, height and the data. And if you have to give the method, co will give you the correlation coefficient. Co will give you the correlation coefficient. In this example that we are working with this, okay, let's have a look at it. This one, easy to go through this one. And this one, admission, okay. And get the head of this one. And I try to get the glimpse of this one. What do you call that one? That okay. See. So you have a GRE score, TOEFL score, university rating, statement of purpose, LOR, letter of recommendation, cumulative GPA, grade point average, research, chance of admit. So those are the factors that we were talking about over here. But in our example, we were talking about the height and weight, okay, simply. But here in this example, chance of height being explained by, let's say that quantitative variable. Quantitative variable would be what? The research, not a quantitative variable. Research is a qualitative variable, see? Group variable, see? Yes or no, see? Yes or no, see? Yes or no, see? You can record that one and yes or no, see? Easily 0 and 1, I'm going to convert it into the way that I see. Go to data, go to research, and then you change whatever you want to change. See? Or that, or you can do like this way. That's a different thing. But what I'm trying to say that here, we are trying to find the relationship, correlation between, regardless of that, this is being continuous or categorical. Okay, see, we can get this one in so many ways. See, there's the same thing undergraduate GPA. Let's say that related to this correlation coefficient means, see, so you have to explain that one correlation coefficient in another way. I'm going to add to this one something. Okay, with one homework, get to this one. Easy to this. When correlation between two quantitative variables do not indicate that the coefficient is positive or negative. Rather, use a description of the variable involved like a greater distance from the home is associated with the more commuting time. See? Like they are, see, involvement, see? Description, quantitative. When we interpret a correlation between a categorical and quantitative, do not indicate that the coefficient is positive or negative. Rather, use a description of the variable involved, like those who were in romantic relationship tended to have more absences from school than those who were not romantic relationship, like that. That how they were differentiated from each other is the correlation. What's the correlation between the two groups in the situation like this? So, in related to this one, since that we were talking about both that models at the same time, we can talk about this one here. Okay, so for my convenience, we have all these packages to put this one. I hope this one works. No, because this package. So first question they're gonna ask about here. It's easy to go through this one and I explain that's easy. Okay. So you will get more depth on that one. So they say that for each of the following explanatory variables, this situation, see, research experience, undergraduate, GRE, TOEFL score, R, B1, B1, DF. Some of these are the ANOVA, not a kind of ANOVA table. They have created their own table. Research experience being how research experience going to affect the chance of admit. How undergraduate GPA going to affect the chance of admit. How GRE going to affect the chance of admit. If a research experience categorical to quantitative, so then you have a group model. Undergraduate GPA quantitative to quantitative, then it's going to be a regression model. GRE score, it's the same thing. GRE score, the same thing. See, you have seen emission data. See, can see GRE score. See, quantitative. See, like that. See. So they were looking for that for each and every category. They were looking for that R, B0, B1, degrees of freedom, degrees of whose degrees of freedom. I prefer that if you put the model, let's put the model one, SSR, or that if, since they have given SS total 2 here. Degrees of freedom, you can go to the error degrees of freedom. There are several degrees of freedom. See, of that category. See. But anyhow, I'm focusing on this one as of now, the R, okay? R. When they were that's the discussion we were having right now. We know how to get B1, B1 and all kind of these. But the R is a new one, that a new one, research experience to this one, chance of admit with respect to research experience. So research experience, what I'm gonna do that since that a 0 and 1, I'm gonna recode it, go to the date, my data, and go to the research. I get the 0, I'm going to replace it. No, since it's a string, I'm going to put that in inverted comma. This has to be replaced by this. Oops, what happened? Record, why they're not working? Chance of admit 1 0 no chance of research factor 1 research factor. It's not what happened. Research, I call it the research factor. So what are we called data research? Data research. All recording should be from, but no. Has to be. There has to be this one. Here has to be in place. One has to. Yes, it. Okay. Why it's not getting there? No, we cannot because these are strings. Has to be within the work in a way. The work sometimes doesn't work. Yeah, I had a serious issue with when I was running this one too. But anyhow, 0, 1. Let's go with the factor, this one. Since we get that one, or we can work with that one. See, yes or no. So there you can see, you can draw there the graph, chance of admit versus this the faceted graph, the histogram. See, yes, no group. If they have a research experience, is there any high chance for them to be that admitted to that program? Chance of admit, see, is no. See, if they go to the average, see, this one has a high average, see, or box plot. See, high chance if you have done the research previously. So what I'm mainly focusing on here, the method on correlation coefficient using C-score. What I'm going to do, I'm going to go ahead and convert this into C-score, standardize. I'm going to standardize this one, and I call C chance of admit. I'm going to standardize. Okay. Okay. See, those are the standardized values. Now, chance of admit, you saw this value. Now standardize. How do you standardize? It's going to go ahead and then subtract its own mean. See, can you remember that? I'm going to show you at the same time. That's the part that I really want to show you. See? See? Okay. Height. If you have a height in this case, that one that instead of height, you have the research, okay? Height minus mean of height divided by standard deviation of height. See? And how do you get this thumb length? Thumb length, mean thumb length divided by standard deviation of thumb length. We don't have to do by hand, then the C-score will do that one. The same way here, that C-score will do that one for us. See? That one, see? See? C-score, convert the research. See? Standardized value. See? Within standardized. Then you're gonna go ahead and then fit in this one. C chance of admit versus C research. See? And then run the regression and then see what are the values. And if you go ahead and look at the slope, so I hope that this didn't work even the last time. See, can you remember? Supernova. Let's install the Supernova. Should get the Supernova. Should get that one. Okay, then you can easily see that when you run this one regression, that the standardized this one regression, you go to the slope. See, slope, see, slope. It's nothing but 55.32. Sorry, 0.5532, 0.5532, 5.532 e to the power of -1, 0.5532. So can I get this one by recalling slope? No, it doesn't work. So not found. But we already installed that one. But something anyhow, that slope of this one is the correlation. This one, this part, see, 0.553. Can I get that one by doing a different way? Yeah, I'm gonna go to the co-function. Chance of admit. I'm gonna go to the original now, chance of admit, not the Z research. And then this is the Pearson correlation, is that strength between that two variables. Then I calculate. See, 0.5532. That's the same thing here. Another way, you go to the core test and then run, see, and then check that one. 0.5532. See, another way you can do this one. You go to supernova. See, correlation coefficient. Okay, let's see this one. Research regression. You run, and you're gonna run the supernova. See, how do you get that one? What is correlation coefficient? See, that's nothing but the square root of what? Square root of 3060. You know that one. Can you remember? Pre is nothing but r squared. Coefficient of correlation, coefficient of determination. Now you take the square root on that one. See? Then you take the square root of what? 3. 3. See? Square root of 3. See? Which is, that's the same thing I'm trying to talk about in the next one. You simply go to pre. See? See? Pre value, see? And square root that one. Okay, I'm gonna see. See. So pre should work. Pre can no. See, cannot because there's something wrong with that. Pre doesn't work too. See. So this one, correlation coefficient using supernova, and they should come under the same method. This one, then correlation coefficient means this one or this one, or you go ahead and run the ANOVA. See, ANOVA in the ANOVA table. ANOVA table, you go ahead and get the what? Pre. You know how to get the pre. Pre is nothing but sum of squared research divided by sum of squared total. So you're gonna get the research sum of squared. See, go to research sum of squared, which is, you know, that already that value. You can read that one, 2.6, 2.40, 4833, and get the residual one. See, you know that value, 5.633. If you add those two and divide by that, divide 2.4833 divided by the sum of those two called the pre. See, that's the pre. And correlation is the square root of the pre. See? It's the same thing. It's the same thing. See? So in a similar fashion, you can get this done in several ways using the, now instead of that one chance of admit, you're going to use the CGPA. See, then you can get the see? Same way. See? We talk about method 3, method supernova, and they go together here too. You go to that one and then get the correlation coefficient, and then do that one or that one or this one. And then you do the same thing for GR. See? You first row, you can do, see, GR is cool. You can get the point, see, the scatter plot, see, scatter plot. And then you can fit in even the, see, that line, see, that line. And here, this one, sorry. Here, see, GPA is the same thing. See, like that. See, it's a scatter plot. But when you have a categorical data, you don't do the scatter plot. You don't do the scatter plot. Scatter plot, you're going to get it done using box plot and then histogram. You did the faceted histogram like that. But here's scatter plot. See? Point or jitter plot. See? To say that you can get a rough idea how they were so close to that fitted line. See? They pretty much see above and below the fitted line. See, by looking at the value of the R, see, you know that by looking at the strength of R, you can figure out how strong their relationship would be. See, would this cause this to have the something? The causation, we don't talk about the causation. See, we don't prove anything. See, we just say simply there's a relationship between these two factors or there those two variables. So here, here this you read the faceted histogram. Then you have a categorical data for X. See, for this one. See. But you do the scatter plot, then you have a both X and Y are quantitative. See, like that. So GRE we did that one. And see. Then if you want, you can go to TOEFL score. See, TOEFL score again. See, you can get the scatter plot. See, you can do the same thing. Correlation coefficient you can find, and you can interpret them. See, and interpret. Okay. So, then Q3, Q4. That's it. It's not. Then how to make a prediction, make a function, and then mainly that we can come to there. But what I'm trying to say that related to that, what I was doing over here, that I was talking about this correlation. See, that's the one that correlation is a Pearson correlation. It's nothing but that's this one. The relation, the measure of the strength between those two. So on the other hand, that we have some ranges for that one. Can you remember we have given that one? So if I show here, there's another one. So see, big patient. See. Regression big easy, regression big easy. See them in this one, get that one correlation coefficient is nothing but the using co-function. You cannot do like that. You have to make the full model. You have to write with the co-function. Or third method, see, using code test. Using pre, see, you can remember pre is nothing but proportional reduction in error. R squared means coefficient of determination. See, coefficient of correlation. R the small piece. See, this one is same as this one. So R is nothing but square root of 3. See, square root of 3. Go to the height model and get the pre. But our pre didn't work over there. I want to double check and see again what's going on. It used to work, but over. That one. Then this one, I want to show you something related to correlation. Okay, related to correlation. Since we're going to talk about that one, I'm going to go back to my one here. So I'm going to go back up over here. I'm using this one. Look at, I'm using the second method, third method, any of these. Let's say undergraduate GPA and admission, chance of admit, quantitative to quantitative. I'm using co-test here, this one. Okay, look at, you see this, there's a table, so many the numbers, see, p-value, degrees of freedom, see, p-value, alternate hypothesis, see, true correlation is not equal to 0, 95% confidence interval, this value, that value, sample estimate is this much. See? That's the value for the correlation, because that's the same value you're going to get it from running which one? I think here, see, this one, see, this one, 0.87. That's the same thing that you got it from running that core test. This one, okay, core test, see, 0.8732. Same thing, see, 0.8732. Same value. So anyhow, that in addition to that one, you can see, they have a range for the estimate. That's called the confidence interval. See, It's a point estimate. You're going to learn about that one. It's the interval estimate. It's a testing of hypothesis. So you have to do three parts in this our discussion. Okay. All the time you have to do three parts. Okay. Three parts. You have to do three parts. See? You have to do three parts. Point estimate. It's a point estimate. It's a point estimate. Somebody asks, what's the point estimate? We're not happy only of the point estimate. We're going to talk about that one in next chapter in large scale. We need an interval estimate. See, 0.8478 to 0.8947, which includes a 0.8732 in between. See, it's a range of numbers we need. We need an interval of estimates. Can I get the interval of estimate? How could I get the interval of estimate? I have only one estimate. Yes, by doing what? By resampling again and again and again and again and again and again. See? So you're going to sample one sample, second sample, third sample, and keep going. You can get many of sample estimates. Those estimates you're going to put within these two bounds, lower bound, upper bound. Not only that, you want to see whether your correlation coefficient equal to 0 or not. You're going to do some kind of a testing. Correlation coefficient is nothing but the true correlation is true means population correlation coefficient. Correlation coefficient normally we're going to denote by capital R or simple R. Okay, capital R or simple R doesn't matter. But population one we're going to denote by rho. See, null hypothesis rho equals 0 versus rho not equal 0. See, degrees of freedom. See, degrees of freedom of model. Number of explanatory variable, number of more predictors than in the empty model. Degrees of freedom. See. So they show the degrees of freedom over here for the model. See, then degrees of freedom for error. Number of parameters. N minus 1. See? F ratio, mean squared coefficient divided by the mean squared error. Same thing that we had earlier. So what are you gonna do over here? P-value is this P-value. See, that's the P-value they're talking about here. That's the P-value they're talking about. See, P-value. Degrees of freedom is 398. It's nothing but if you go ahead and run a supernova here for any of these, let's say, see, sorry, we are in GPA. I'm gonna run supernova. See GPA not found. Equation first we have a one that yes, the CGPA equation. Okay, is that nothing but the sum of square error. This shows the sum of square error. And the p-value. P-value. See, p-value not for that one, p-value for that. See, p-value. See, t-value, p-value. See, where this t-value? T-value I don't see here. See, I don't see here. We have a method to get that one. We can talk about that one next time. Okay, I'm gonna just expand this discussion in that direction as well. See. So, yeah. But mainly this is the test, how to run the test and how do you get those values even that I can. But they're not gonna ask for those values in our that homework, but it's better off you to get that knowledge on pretty much everything, broader knowledge or better. This one you can see. Fill in this one, B1, B1. Degrees of freedom you get for error. If you want, you can get for error. Yeah, put for degrees of freedom for error. Yeah, degrees of freedom for error. Let me see. I can keep the same format error. Degrees of freedom for error. Error only because you cannot write any all of them. This is a research experience with chance of admit. Get the run the ANOVA table, get that one. Run the regression, get this one. Run the regression, get this one. Run the get this one. Oh, that's so many methods. Regression, you get this one. ANOVA table, you get all these, all the way up to here. From here to here, all ANOVA table, supernova. From here to here, regression. From here to here, you can run test. Easy, one of them because there are so many methods to get the correlation coefficient. Or test if you want or test. This one. Dot test. This one from here to here, see, you can get the regression from here to here, supernova. From each and every one, fit in over there. And then interpret and put it over here, their interpretation in the way that they describe over here. If it are how to explain, if it is B1, quantitative explanatory variable describe whether the outcome variable expected to increase or decrease and by how much. When the interpreting the categorical experiment describe whether there is a mean difference between those two categories. When interpreting B not for quantitative experiment, describe what the expected outcome when the explanatory variable is zero. When categorical, you can say describe what is expected with the outcome those who have a predictor score zero. Like that. What model is the best model according to PR? What model would be the best model according to F ratio? Which model explains the more variation for degrees of freedom? See, degrees of per degrees of freedom. See? Per degrees of freedom. See? Per degrees of freedom. See? Sum of squared error. Per degrees of sum of squared error explained by the model per degrees of freedom mean square regression. See? Sum of squared error explained by the model per degrees of freedom, if you take into account, it's called the mean squared regression. That one you can easily find. Okay. In which model? The best model. In best model, okay, you go to the best model. You can check out of all these which model has like a highest G3, which model the highest this one. All this is consistency, CGPA. Then go to the CGPA and look in this one and explain that one. Okay. Later on, we're going to make a function and then even check that that particular person's whether being admitted or not like that. Okay, we can check that one too. We can talk about that one next time and then continue the same discussion. We have plenty of time to, because after that one, there's not that much. Main thing is a correlation here. Main thing and the ANOVA table. You are very familiar with the ANOVA table. See? So they very elaborate to explain. We can add more explanation to this one. Okay. That's it. That's all we have to do. Okay. There's nothing too much here. Only thing that main thing that you're gonna fit in that regression model. You're gonna run supernova. You're gonna compare contrast, and then you're gonna get the correlation. Correlation we can get it in several ways. See, we have plenty of time. We still have 2 more days, so we can just We can go through this one again and again and then solidify what we have learned. And then I have to make sure that my pen is working properly, that something on with that one. I can't write anything. So do you guys have any questions, anything that, so Wednesday we're not gonna have a class, we're gonna have a class, instead of Wednesday, we have that class on Friday, okay? And Wednesday, Thursday, we're gonna have class as usual, same time, okay? So if you guys don't have any question, I'm gonna let you go. You guys have a good night and then stay safe and be well and see you guys on Thursday. Take care, okay? Good night. Thank you very much. Take care, bye-bye. Thank you, take care, bye. Thank you very much. Yeah, thank you, good night. Thank you very much. Yeah, take care, good night. Yeah, thank you very much. Take care, bye. Thanks, take care. Thank you. Good night, take care.